In problem 12.53, we have a pole which rests on the side of a slope. And what's keeping this pole from falling down the slope is there's a frictional force at the point of contact with the slope. There's a tension force that overcomes the torque produced by the center mass of the pole. And so we would have to use equilibrium to determine how much friction would be necessary to hold this pole in place. The variable given is the angle and the mass of the pole. We could put the length of the pole also. It turns out that really the answer only depends on the angle. We're to find the coefficient of friction that would hold this in place. If it's not enough, the Fg would pull it down. If the friction force is not enough, or the coefficient of friction is not enough, the pole at the base would slip down the hill. So we've got to establish equilibrium. And I'll start out with the x equation first, summing the forces in the x direction. And that is that minus the force of friction, minus the force of tension in the x direction, plus the force of gravity in the x direction, they must add up to be 0. Putting in the proper angles, Ft times the cosine of theta gives its x component, and Fg times the sine of theta gives its x component. Here I've set those on the other side of the equation. So I have an expression for the force of friction. To get the normal force, which we need to find the coefficient of friction, we sum the forces in the y direction, and we get Fn minus Fty, its component, and minus the y component, Fg. They must add up to be 0. Okay, plugging in the components in terms of the angles, Fn would be equal to the y component of Fg, which would be cosine of angle times Fg. And the force of tension in the y direction, that's just this component right here, so that would be Ft times sine theta. And since I have Fn, then the force of friction is mu times Fn, so mu times this term up here, there's the force of friction. Since I have the force of friction, two expressions, this expression and this expression, I'm going to set them equal to each other so that this term right here is here, and the term up there is here. And the only thing that's keeping us from really solving this is to get rid of Ft, and Ft can be put in terms of Fg. To do that, I've got to sum the torque. So this is the torque equation right here, okay? We get a torque produced by Ft by rotating the length of the pole, that vector, into Ft. And that would be equal, well, here down here is probably the best place to look at that because I got the angles labeled. That would be L crossed into Ft. Here's the angle here. So it'd be Ft times L times the sine of this angle, but the sine of this angle is sine beta because they're supplemental angles. So I'm going to go put FTL sine beta for the torque produced by Ft, and that's a positive torque. It comes out of the board because we rotate L into Ft. Fg will produce a minus torque. It's displacement from the origin, and I'm summing the torques about this point right here is L over 2, pointing in that direction, times the sine of this angle right here, sine gamma times Fg. And so here is that contribution to the torque. The sum of those two must be equal to 0. Now you'll notice that I've got sine beta here, but beta is this angle, and the sine of beta is the cosine of theta right here. Okay, so I'm going to replace sine beta with the cosine of theta. So I've got FTL cosine theta and that's equal to FG times L over 2, and that's supposed to be sine of gamma, but the sine of gamma is a sine of theta because they're supplementary angles. Okay, so I can just put a sine theta there. Okay. Now that I have FT, I can replace, I can put this value of FT into here and here in the coefficient of friction expression. And if I do that, I'll go ahead and put them in here. Here's FT right here, and here's FT right here. And the rest of the problem involves just isolating mu in terms of what will end up being a function of the angle. To start you off, notice if I divide everything in these two expressions right here. Oh, by the way, the FG can go out. You can see that. You can eliminate the FG. So once you've done that, divide everything by cosine. And so you'll get a cosine. That sine is that sine. There'll be a tangent here. This cosine theta will eliminate that cosine theta, and you'll just have a tangent here, and that cosine under here. This whole expression will be in terms of the tangent, with the FG's gone. So you'll see that you should end up with a trigonometric answer in terms of, most likely, the tangent of the angle. So you should be able to plug into that and get that final expression.